Okay, are you ready to continue? As I warned you about, we have another way of completing. It's just, the hypothesis test is the hypothesis test. We have in the practical use of it two slightly different ways of sort of completing the business. I have shown you one way, the p-value way, in which we take the difference between the data and the hypothesis, turning into a probability that expresses the oddness of the data in light of the hypothesis. How likely / unlikely is the data if what they claim is true? That's how we look at it. I would say it's the common sense way of looking at it. If we go back, I had the stone in the sand. Let me take a more naive. If you have the coin tossing situation and someone has a coin that you believe would be asymmetrical, sort of cheating on you, how would you do it? How would you think if you want to check the claim that this is a symmetrical coin? If you want to prove it to be not symmetrical, the alternative, you would start flipping the coin. You would see I get 9 out of 10, or let me say 14 out of 15 heads. How would you think? 14 out of 15 heads is definitely unlikely if the 50-50 claim is true. So that's the p-value you found there. There's the p-value again. What I see is unlikely given the claim, given the hypothesis that is there. So I have to reject the hypothesis. If what I see in the light of this hypothesis seems unlikely, if what I see seems likely enough, I would just have to accept the claim. That's the hypothesis test, right? Well, there is a slightly different way of finishing the story. Instead of 3 and 4, in 3 and 4, we calculate the p-value, we find the p-value and we compare it to the alpha level. We could sort of turn it around in a way and find out before even finding the p-value, we could say, what is the critical value? How far away can we accept to be? Where is the limit to how far away is acceptable? And if we go beyond this, it becomes critical and we would reject, right? So we could, before even looking at the data, we could find out, knowing the standard normal, we can find out, and then I jump to the part that I have I wanted to show you this list. What I'm jumping into now is this part 4, where we finish off the hypothesis test by finding the critical value. Now, here we have to keep our tongue straight in our mouth, if we can say that in English also. We say that in Danish at least, not like that, but it depends on the situation how we claim what is acceptable and what is rejectable, what is critical. It depends again on the one-sided, two-sided thinking. Is it acceptable is it sort of rejectable, you could say, both to be too small or too large, or is it only rejectable, non-acceptable, to be too large or, for instance, too small? Either too large or too small or two-sided. This is where it comes, these awful tables, and you're going to see a lot of these awful tables in what comes in today and later in the course. This basically says that if we are in a one-sided to the one, and this is our example. This is our example here, right? So, in our example, we can use only one row in this table. In a given context, we are only one place. This says that the critical value is set alpha in this case. What does this mean? It means that if alpha is 5%, then we find the value, set alpha is here, we find the value that has 5% to the right of it. That is the sort of the threshold between what is acceptable and what is rejectable. Or that is what we call the critical value. Exactly where we would stop accepting and where the deviance would be rejectable, critical. That's the wording of it. So, let's do it and then I go back to the table. Let's do it in our case. What is set 0.05 in our case. What is the point in the standard normal distribution having 5% to the right of it? Do you remember that? It's a trick question this time. Since the one I said you should start with remembering is not this one. The one I said you should remember on the top of the list is the 2.5% point, which is the 1.96, right? This is the 5% point now because we're having this one-sided view of the situation. So we are going to look for the one-sided. Let me just, for once, have a table today. Actually, whoa, I'm looking at a standard normal. Why am I looking at the table 4, the t-table? Well, because at the bottom of the t-table, we have the normal, some of the normal quantiles. Which one was I asked was relevant here? It was the 5% point we should find. The 5% point of the standard normal is 1.645, right? 1.645. Let me Q norm of, what was the probability? 5%, so Q norm of 0.95, the same number, 1.645, if you want to be exact, 645. This is the critical value, right? If I observe a standardized set above this, so this region is accept, this region is reject, right? It shows a story here. It shows that even before we look at the data, we can make up this, we can put the whole continuum of possible outcomes of the experiment. We could put that into two cups, two bowls, and saying, if I commit a study, an experiment, telling me that the set, and what is set? Set is the x bar minus mu naught divided by s over root n. Or, sorry, this is what's going to be set, or the one where I just plug in the known variance. We're going to see that by the end of this little talk here. If this set is here, that is not very far away, you know, not very far away from the claim, then we accept the claim. If we go beyond 1.645, if the data is larger than 1.645 away from the hypothesis, measured like this, then we reject. I think it makes good sense, right? Being far away from the hypothesis, we reject the hypothesis. Being close to the hypothesis, we accept it. Common sense. We just have to be intelligent about where do we put the limit between being close to and far away, right? This is where we use probability, to make an intelligent limit between close to what the claim is and far away. There's only those two options. Either we accept or we reject. No in between. Question?
Yeah. The three sets, are they the same? Like the set over an 05, is it the same as the two you just wrote down?
You ask me whether set 0.05 is equal to... No, it's not. The set is used in different ways here, the set. Here, I use the set, it's difficult to see. Actually, it's a small set here, used in the sense that is seen. Then I should maybe find table. Let me show you. Just here we have table 3. Here I have table 3. These are the sets that I use there. And for instance, I can see here that set 0.08, for instance, equals 0.5. This is now I'm just doing something out of my head. I shouldn't do that too much here. This is the way I use the set. here. Over here, the capital set is used as the set, the one we compute from the formula given. I'm jumping back here. Here's the formula. Here's the capital set used as the formula for the t for the test statistic here. Another question.
Shouldn't it actually be set 0.95?
That's a good question, and this is a matter of decided notation in the book. You're right. The way we use the percentile and quantile naming, this is, you could say, this is the 95% percentile of the standard normal. You're right there, and this is this is then Q norm. That's also why I said this is in R. They use this notation Q norm. But the book is consistently, through all distributions, using the opposite notation. So what they call set 0.05 is just, we just have to learn that that is the name of not the 5%, but the 100 minus 5% percentile. So it's just a decided notation of the book. It's not because they don't know what the percentile is. And the reason for making this decision in the book is that when we do the statistical things, we very often are looking at the right-tailed probabilities. So it's just a decision made that that's the notation in the book. And it's consistently through all the tables and the distributions. Yeah. Yes. So in our case, if I should finish the hypothesis test once again, I already finished it once, then I should see that I observe, I emphasize observe, a set of I observed a set of 1 point, what was the set originally in my example? The one I observed, 1.66. So, the decision to be made is the one that is given to us in this table. That's why I'm now going back to this awful table. The table tells us that if my observed set is larger than the critical set alpha, I reject, right? That's just what's in the table. If the observed set is too far away, I reject. So, in our case, we reject. Of course, we knew this should be the result since we already did that on the same risk level. So the tables, generic tables like that, takes all situations into account. So the middle part of the table covered my specific example here. In another example, maybe the things could have been turned around. So in another example, maybe I should reject if the observed set is too large to the left, too long to the left, too small. Then I would reject in this case. Or in the two-tailed case, and you'll have the option to practice this a little bit. I cannot go through all examples here. I don't have time for that. So you'll have to do it yourself in the exercises. In the two-tailed situation, I would reject if my observed thing is either too large, that is too far to the right, or too small, that is too far to the left. And then the probability is sort of not, we don't have all the 5% in the relevant side, we have 2.5% in each side. So if we go beyond the 2.5% point, either to the right or to the left, we would reject. So that's the sort of the challenge here, is that we have three different situations depending, but I mean, the good news is in a given context, we only have one of those coming up to us in our phase, right? We just have to decide which one are we in. One-sided right, one-sided left, or two-sided. You cannot decide after the data, you have to decide before you look at the data. This was practical hypothesis test, the critical value approach.